Why are we paying for several AI subscriptions and sending private information across the internet when some of these tasks can already run on the laptop in front of us? No internet, aeroplane mode on, and Wi-Fi is off as well. And I have physically unplugged the Ethernet cable. And let me prove it. This laptop will not be able to reach any of the websites or go on the internet. And as you can see, I can tap the Dino and play play the game. Now watch this. Hey Sarah, can we go ahead and move the Tuesday meeting to actually make it Wednesday, somewhere around 3 p.m. And I have a transcription which is coming up, and I can show it to you by pasting it right here. So it's coming in the memory as well. Now this is not only a speech to text application. The application removes filler words, added punctuation, understood that Tuesday has to be corrected to Wednesday, and it did all of that without sending anything to the internet. No cloud API, no request traveling to a remote data server center, and no company charging for every sentence I dictated. This raises a larger question. Why are we paying for several AI subscriptions and sending private information across the internet when some of these tasks can already run on the laptop in front of us? Most AI applications follow the same basic architecture. You speak, type, or upload something into an application. The application sends that information across the internet to an external model. The model processes it inside a data center, and the result is sent back. The architecture is convenient, and for complex work, it can be the correct choice. Large cloud models are powerful, flexible, and capable of solving very broad problems. But this architecture creates two recurring costs. First is the money you pay. Second is the information you provide in order to use the service. Let us begin with the obvious cost, the subscription. Imagine an AI dictation application costing approximately $12 per month. $12 sounds small, and it is approximately the price of a couple of coffees, but this is rarely only AI subscription somebody has. You may also have an AI meeting assistant for around another $20 per month, then perhaps an AI writing assistant for another $20 a month, and a productivity assistant for another $20 per month. Individually, every amount looks manageable. Together, those four applications cost $72 every month. That becomes $864 every year for one person. Keep the same subscription stack for 5 years and one person pays $4,320. For a 10-person business, the same subscription cost goes up to $8,640 every year. Or for 100 users, the figure becomes $86,400 every year, or $432,000 over 5 years. These numbers are illustrative, and actual price vary, and many services provide valuable features beyond running a language model. But the calculation shows how several inexpensive tools can quickly become permanent operating expense. You may be paying separately for transcription, meeting summaries, writing assistance, document cleanup, even though those are closely related language processing tasks. And a local model creates the possibility of performing several of those narrow tasks through one system running on hardware that the user already owns. The application still costs money to build and maintain and support. The computer also consumes memory, processing power, and electricity. Local AI is not completely free, but an external model provider is no longer charging for every sentence, summary, correction, or transformation. This can support a one-time purchase, a much lower subscription, or an AI feature included inside another product. But the subscription stacking creates another problem that may be more important than financial cost. Every subscription can also become another data relationship. The dictation application may receive your voice. The meeting assistant may receive entire workplace conversations. The writing assistant may receive your emails, proposal, reports, and documents. The productivity assistant may receive your searches, questions, work context, and browsing history. You are therefore not only paying for 4 subscriptions, you may also be trusting 4 different companies for 4 different parts of your working life. Each service may have its own privacy policy, retention period, infrastructure, account settings, and approach to model improvement. Some providers offer strong privacy controls and enterprise protections. Others made different rules depending on product, subscription plan, or account configuration. This does not mean every cloud application is unsafe. It means the user has more providers, more accounts, more policies to understand and manage. The practical problem is that most people do not read four separate privacy policies before pressing a microphone button. They may not know where the information is processed, how long it is retained, where logs are created, or which settings control future use. And the information involved is abstract. These applications can receive your actual words, voice recording, customer names, and internal conversation. A dictation may contain financial figures, legal information, addresses, personal details, confidential plans, or something spoken accidentally. A meeting assistant may receive an entire document when user only wants one paragraph rewritten. With cloud processing, some of the information must leave the device so that a remote system can process it. Once information is transmitted or collected, it must be governed, secured, retained appropriately, and eventually deleted according to applicable policies. Every additional provider can add another account that could be compromised, another integration that could be configured incorrectly, another policy that may change later. This is not an accusation against any particular company. It is a consequence of distributing information across more systems. Local processing changes this. The audio can be captured on device, transcribed on the device, and cleaned on the device. The finished text remains on the computer unless the user deliberately chooses to send it somewhere. Instead of asking several companies to promise that they will protect the information, the architecture can be designed so that those companies never receive it. That is the difference between privacy by policy and privacy by architecture. A privacy policy explains how collected information should be handled. Privacy architecture reduces how much information is collected in the first place. A server cannot expose a recording, transcript, or a private document that it never received. This is particularly valuable for people working on customer records, legal material, financial information, and intellectual property or internal business documents. It is also useful on an aeroplane, also during travel or in a rural location or inside working environment where external connections are restricted. Local AI can therefore address three problems at once: recurring subscription cost, cloud dependency, and unnecessary data transmission. But this only works if local model is capable enough for the task. That is where choosing the right problem becomes important. Let us take the lid off and look at what actually is running inside the laptop. The application uses Rust and React wrapped inside Tori. Rust handles audio processing, audio capture, model execution, operating system integration. React provides the interface. The interesting part is the AI pipeline. It uses two models. Each model has one clearly defined job. The first model is Whisper, not the cloud API, the model running locally through Whisper, CPP. Its job is to convert sound into text. The model used here is a 148 megabytes model, which you can see it's installed and running right here. It's running on the computer without calling any external speech to recognition services. The second model here, which is used, is Gemma model, which you can see right here, which is called Informata. Now, Gemma 3 is a 1 billion parameter model, handles fast dictation cleanup. A larger 4 billion parameter handles more demanding work such as meeting summaries. So there are options which are available based on your computer's memory. The 1 billion parameter version is approximately 800 megabytes. The 4 billion parameter version is approximately 2.5 gigabytes when quantized. These models are dramatically smaller than the frontier models operating in major data centers, but the model size alone is the wrong comparison. The correct question is not whether this model is intelligent as the largest model available. The correct question is whether it is capable enough for a specific task. I'm not asking this model to understand the entire internet, perform broad research, or build a complete software product. I'm asking it to take information already present in the input, make that information clearer, and better structured. That is a smaller problem. Small language models can be extremely effective when the problem itself is narrow and clearly defined. This is a central lesson. Define the problem first, then choose the smallest model that solves it reliably. The application works in 3 layers. Each layer has one clear responsibility. Layer 1, Whisper. It converts sound into rough transcript. It does not try to produce a polished email or understands every possible intention. Layer 2 is Gemma. It converts rough text into good text. It removes filler words, handles corrections, and changes the structure according to the task. Dictating an email produces an email. Dictating notes produces notes. Dictating a list produces a properly formatted list. Layer 3 learns from users' corrections over time. And I will return to that because it's another advantage of running locally. Separating the system into layers also makes failure easy to identify. If a person's name is transcribed incorrectly, the speech recognition layer may be responsible. If the words are accurate but badly written, the formatting layer may be responsible. When one large language model and one enormous prompt handle everything, debugging becomes guesswork. With layers, every failure has an address. There is an important layer here, which is optimization. And you can see in the screen right here, many dictations do not need a language model at all. Normal code can remove obvious filler, fix basic capitalization, and handle predictable punctuation. This can run into approximately a millisecond and consume far fewer resources than activating a language model. The language model activates only when the text generally requires interpretation. For example, a spoken list or a correction such as actually or scratch that. In a cloud system, developer reduce calls to save money. In local system, we reduce them to save time, memory, battery, and user patience. The principle is the same. Do not use an expensive tool for something simpler code can already perform reliably. Smaller models are useful, but they are not miniature versions of frontier models. They have real capacity limits. During development, a 1 billion parameter model produced a meeting summary containing a $12,000 figure and an August date that nobody has mentioned. It had copied those details from a worked example inside my own prompt. I had explicitly told it not to copy the example's fact, it copied them anyway. The solution was not adding more instructions. The solution was removing the copyable information and replacing it with neutral placeholders. That taught me an important lesson. You cannot always prompt your way out of a capacity problem. Sometimes context must be redesigned. Smaller models also become much more reliable when their output is constrained. Asking a model to return a valid JSON and retrying whenever it fails is fragile. Instead, an application can use JSON schema to restrict which tokens the model is allowed to generate. Invalid output is not simply detected afterwards. It becomes impossible to generate in the first place. At this model size, constrained decoding was one of the largest reliability improvements in the entire system. So let us return where we began. This laptop is now come back into a Wi-Fi mode, and I just wanted to show that small language models can just not be used locally. You can use on your regular applications. So in this example, I'm showing Codex from ChatGPT. Now, Codex, the problem with Codex is it does not have a voice extension for VS Code right here. So if I go ahead and start the transcription, let me go just dictate one more instruction. Hey, can you go ahead and look at a plan here and suggest what can be done regarding a couple of errors which are coming in for security vulnerability. Now, as you can see, it has already gone ahead and pasted the text which is there. Let me take an email example. Now, this is my email, and let me go ahead and dictate a list. Hi, Sam. Can you go ahead and make a list of things which we need for Friday's party? The first one is we need some balloons. The second one is we would need some snacks. The third one is let's make sure the invites which we have suggested has been sent out. And you can see it has formatted the email which we have suggested. So the transcription and the formatting worked again with no cloud requests, no per token model charges, no private recording sent out to the company. The argument is not that a local AI can replace every cloud model. It cannot, and it does not need to. For complex research, information, broad reasoning, and difficult multimodal tasks, a cloud model may remain correct choice. But for transcription, extraction, cleanup, structured, rewriting, a local model may already be sufficient. The first question is whether users should pay $12 for dictation or $20 for meetings, $20 for writing, and another $20 for productivity when some of these tasks can run through one local system. The second question is whether recordings, meetings, emails, document search, and search context need to be distributed across four different providers in this case. Do we need to actually send it to the internet? Open models such as Whisper, Gemma can run on ordinary computers, and they can work without an account, without a permanent connection, and without charging the individual for every token. They are not appropriate for every problem, but they are already capable enough for many narrow, repetitive, and clearly defined tasks. Start with a task. Everything the model needs is already present in the input. Build the deterministic path first. Use a normal code for predictable transformations, and activate the model on when interpretation is necessary. Test the model on your real examples, constrain the output, and select the smallest model that solves tasks reliably. You may not need the largest model in the world. You may not need 4 permanent AI subscriptions, and you may not need to send every private word to somebody else's server. Sometimes the smartest AI decision is choosing the smallest model that solves the problem and keeping both the cost and the data under your control. Links to the models, tools, and projects shown here are included in the description. Thank you for watching.